In this video, continuing to look at a 3D spherical potential, I'm going to talk about the radial part of the equation. In the previous video, I talked about the angular part, which gave us the spherical harmonics. In this part, we're going to be talking about the radial part of the equation. And so what we're looking at, once again, is a sphere. So it's a sphere where inside we have V equal to 0, and then outside is V equal infinity. And so we have the radius of it as being equal to A. So I guess we could say the radius R is equal to A. And so we needed the boundary condition that that the wave function goes to 0 at A. And so that is what we're going to be working with here. And remember, the spherical harmonics are essentially, if we think of this sphere as like an onion, then the spherical harmonics tells us each layer of the onion, sort of the outside of that layer, what the wave function is, where the radial part is going to be telling us what is happening as we go from the center to the outside. And so you can think about it, if we have a graph like this, that this would be the center at 0, then the x-axis would be going further away until we get to maybe some point A here. And then the y-axis is telling us essentially what the value of the wave function is there. And so we will see, I guess, sort of a spoiler alert, that this is where those shapes of the s orbitals and p orbitals come from, where the s orbital will look something like this and then sort of go to 0 at some point, and then the p orbitals look more something like this, where if you remember, the p orbital has those two lobes like this, so this would be one of those lobes, and the s orbital is a sphere, and so it would look like this if you turned this into a three-dimensional object. Then it would look like a sphere. But anyway, that's getting a little ahead of ourselves, so let's talk about our radial equation. So here is what we ended up getting in the previous video after doing a separation of variables, where here in this sort of brownish color is the angular part of the equation, and then in red was the radial part, which in the previous video I said I was going to talk about in this video, so that's what we're going to talk about. So here is the radial part, and we have it set equal to this constant, the same constant that we had our angular part set to. And so then again, kind of going through this math quickly, and again, if you are interested in sort of solving the differential equations, then I would recommend looking at my differential equations playlist. This right here is essentially trying to get us to a point where it is the differential equation for the well, it's going to be for this, it'll be the spherical Bessel functions. For a hydrogen atom, it's the Laguerre polynomials. But anyway, we're trying to get our Schrodinger equation into a form of differential equation that we can then solve. But anyway, so to do that, we multiply both sides by r, then we move some things around. So we distribute this part here into the energy and potential term here. Then we end up subtracting this L times L plus 1 times R on both sides, and then subtract the E times this on both sides. And then we do a change of variables, which I've said before, especially when we get to the hydrogen atom, this is going to be something we run into a lot, where we do change of variables and different substitutions. But essentially what we're doing is trying to get rid of this sort of big, ugly looking thing here. And so by doing that change of variables, we kind of get rid of that, and then we can cancel some r's, some of these r's on here. So essentially what we're doing is we're changing this big R here into this U, which is a function of R. So the big R is the function, and then the little r is the radius of our potential here. And so we are changing it into this U, which is a function of R. And so this is what we get when we make that substitution. Then because the big R is U of R divided by R, we can then cancel some of these small r's, which gives us sort of a nicer looking equation. Then we multiply both sides by this minus h bar squared over 2mr, which will cancel out these parts right here, and so we end up getting into this form. And so now I'm sort of changing colors on this part here, because what that is a centrifugal term which is added to our potential, and that centrifugal term essentially just like a centrifugal quote-unquote force, because the centrifugal force isn't really a force, but I'm not going to get into that here. It sort of looks like a force to us because it's kind of pushing things outward, and that's what's going on here, is that this is pushing our particle outward, sort of away from the center and towards the edge of the sphere. And so we get this potential term, so V effective is equal to our potential plus this centrifugal term here. So inside the sphere, our V is equal to 0, because that's kind of how we define it, where V is equal to 0, and then everywhere outside it's infinity. So we can set our V equal to 0, and then multiply both sides by minus 2m over h bar squared. And this E here gets multiplied by that minus 2m over h bar squared, and we end up with this here. And so we are also sort of, so we set this to 0, and we're moving this centrifugal term to the other side. And so we end up with this here. Then we do this substitution where we set k equal to the square root of 2me over h bar squared. And so this all gets sort of absorbed into that k. And since we define it to have this square root and the h bar being without the exponent, we have the k be the k squared here. Then so if we want to solve this for L equals 0, what we end up with is this as our solution. So this A times sine of kr plus B times sine of kr. But since our U here is defined with this this divided by r here, because what we're actually trying to solve for is this r. We've just made this substitution, but this means that this cosine of kr is actually a cosine of kr over r, since we are using this u here as our function. And so cosine at r equals 0 is 1, but dividing by 0 makes it blow up to infinity at r equals 0. So B must be 0. But sine of 0, so when r goes to 0, that becomes 0, is just 0. And so it does not blow up at infinity, because we, well, yeah, because we just end up having 0 divided by 0. But anyway, the boundary condition, which is that the wave function must be 0 at the edge A of the sphere. Remember, we said that that the wave function at the edge of the sphere must go to 0, means that our sine of kr must be equal to 0 at the edge, because our wave function, which is what this is what needs to be 0 at the edge. And so our Ka has to be equal to n times pi, where n is some integer, because sine of pi is equal to 0. And so sine of pi of any integer multiple of pi is also going to be equal to 0. And so our allowed energies for L equals 0 are defined by this. So we have our k squared, which is, so if we divide both sides of this by a, then we have our k equals n pi over a, but it's k squared, so it's n squared pi squared over a squared, and then multiplied by this h bar squared over 2ma. And so that's for integer multiples of our pi here. And so this down here I did just sort of as a sanity check to show that what we're doing is correct, because our k squared, remember, we define k as the square root of 2me over h bar, so k squared is 2me over h bar squared. So if we plug that in for our k squared up here, this h bar will cancel with this h bar, so we end up with this. Then this 2m will cancel with this 2m, so we get e. So our e at certain m's with L equal to 0, that's what the 0 is there, is equal to e. And so the sanity check shows that we are in fact saying that our energy will equal energy. And so if we normalize our a, so remember we had this a here in front of our sine of kr on the solution to our wave function. So we end up with, if we normalize it, we get a is equal to 2, the square root of 2 divided by a. Remember, a is the radius at the edge where our v0 instantaneously goes to v infinity. And so yeah, we have our, this then is our solution here. So our u, which is a function of r at different n's, so that's what this n here is at with L equals 0. That's what that 0 down in the down there is equal to the square root of 2 over a times our sine of n pi r over a. And so this, it's a function of r, and so what this is telling us is we have maybe n equals 1 here, so then it would be pi times r, and so once r gets to some integer, once it gets to 1, for instance, well, actually it'd have to be equal to a, because r over a here would have to be equal to 1. Then that would make it pi, or sine of pi, just sine of pi, so that would be 0. And so that's how this r, once this r gets to a, once this r in the numerator gets to a, then it cancels out with the a in the denominator. And so then we would have sine of pi, which is 0, and that is how our wave function goes to 0 when r equals a. But then that's all pretty simple enough if we have our L equal 0. But what happens if our L is not equal to 0? Well, then we get a solution that looks like this. And now we have, instead of sine of kr, we have this this spherical Bessel function and this spherical Neumann function of Kr. So the spherical Bessel and spherical Neumann functions are sort of acting the same way as our sine and cosine are in this instance. And so just like with the sine and cosine, the spherical Neumann function blows up, and so we need b equal to 0. And so we are going to look at just the spherical Bessel function. By the way, I think the Neumann of this spherical Neumann function is a different Neumann than the famous 20th century John von Neumann. I think it's a different, earlier Neumann. But anyway, that's beside the point. So what we have here is our wave function is equal to a times r times this spherical Bessel function, which is taking the place of our sine function in here. And so we need our spherical Bessel function when r equals a to be equal to 0, because that's our boundary condition, where a is the distance of this to the surface of the sphere in all directions. But the spherical Bessel functions don't have nice zeros. Like, we don't have a nice 0 the way we do with sine, where sine goes to 0 when it's sine of pi. We don't have nice zeros for the spherical Bessel functions like we do with sine. And so they needed to be computed numerically, but we can represent them as this beta sub nl, so for the different n's and different l's. So for the nth 0 of the nth spherical Bessel function. So we have our k equal to this beta nl over a. And so the allowed energies, so the energy E sub nl is equal to our h bar squared over 2ma squared, because now we're multiplying by the a in this denominator here, times our beta squared sub nl. And so if we put that together with our spherical harmonics, what we end up with for the solution to our wave function here as a function of the radial and the two angular parts is equal to this ANL, which is a constant determined by normalization, times our spherical Bessel function times our spherical harmonic here. And then the n down here is our principal quantum number, the L is our angular or azimuthal quantum number, and m is the magnetic quantum number. So those are where those quantum numbers that you will learn about in like a general chemistry class actually come from, is from solutions to the wave function here. And if we make everything more explicit, so adding in all this stuff here in blue, which is this is the spherical Bessel function right here. So this is the generator of the spherical Bessel function. Then remember, this big radical here was a normalization for our spherical harmonics. And so this sort of bright purple here is the part of our spherical harmonics. So it's the part of the associated Legendre polynomial, and then here in the teal kind of color is our Legendre polynomial. All right, so then the question is, how do we interpret all of this? So to interpret the radial part, I'm going to use this calculator here, and this was put together by a person who runs a channel, and it's from this video here. So it's by TMP Chem, and it's a really awesome channel for learning about all this stuff. And in this video, he goes through this this calculator here for all the radial functions. And this is actually for the hydrogen atom. So it's actually using the Laguerre polynomials, which I have not gotten to yet. Getting to that will be in the next few videos. But the principle is the same. This is using the Laguerre polynomials. This is the Wikipedia page for that. But like I said, the principle is the same. But we can just imagine using the spherical Bessel functions instead of the Laguerre polynomials. But anyway, so when we have the radial of r, so NB, the big N being 1 and the L equal to 0, we get a function that looks like this. And the origin here, or the y-axis, would be sort of the center of our sphere. And then we would be going outwards from the center of our sphere as we go from here along the x-axis. And so we see this function which exponentially decays down. If we looked at this in 3 dimensions, it would look like a sphere, which is what our s orbital, which is this right here, would look like. By the way, this here is the spherical Bessel function. So we could see this in red would be sort of the same as this here from our Laguerre polynomials. But then if we look at, if we get rid of that, if we look at the next up, we would have this, which we can see this has these 2 lobes, and that would actually be the S2, the 2s orbital. So this is the orbital for elements like hydrogen. All right, so I found this on the atomic orbitals Wikipedia page. I think part of it's getting cut off at the top there. All right, so this is the n equals 2, L equals 0 right here. So that is what we have right here. So you can see that we have the wave function here. It goes to 0 right here. Then we have more wave function right here. And that's what you can see on this. So this bright part here in the center is this part right here. And then this dark part here would be where we hit the 0 right here. And then we have this part on the outside, which is this part right here. And you can see that this sort of dies off a little bit slower. That's why it ends up being larger. And so we can imagine this plot right here being sort of looking at starting from the origin and going this way in just a line over this entire thing. But if we wanted to look at it in 3 dimensions, this part right here would be a sphere. Then we'd have sort of a sphere of 0 wave function surrounding that, and then a sphere of wave function surrounding that, which would be this part right here. And then we can look at the r sub 2, and then L equals 1, which looks like this. And so this is that lobe of a p orbital. So it looks like this. So this is the 2, 1, and it looks like this. And so you can imagine that we start at the origin, which you see there's 0 there, so it goes to 0, and then it comes up and goes around here. And we see we have this node right here, and that actually comes from the spherical harmonics. In the spherical harmonics, remember, we are looking at the surface of the sphere like this. So this has L equals 3, but what we would have is something that looks more like this. So if we ignore these sort of lines of longitude on here, we would have a top that is all positive and a bottom that is all negative. And this line around the equator would be 0. There would be 0 wave function there. And so that is how we end up with zero wave function right here. So it's essentially like we are taking this function right here and multiplying at each point. So each point on the x-axis is being multiplied by our spherical harmonic. And so that is how you end up where the spherical harmonic is highest, which is where this is right here, this bright part. The spherical harmonic is highest, and we're multiplying it by this right here on our radial part of the equation. And so that is what we are doing. Yeah, right here. So we are taking our spherical harmonic and multiplying it by our radial part of the equation. So where this goes to 0, then the spherical harmonic multiplied by 0 will go to 0. But where this is highest, our spherical harmonic multiplied by that higher part of the radial equation will then multiply together. But then where we have the radial equation highest and our spherical harmonic goes to 0, then the wave function, this multiplied by 0, will be 0, and that is how we end up getting 0 wave function around here. And so then we can look at, so this is the s orbital in the so the 3s orbital. So we see we have wave function here. It goes down to 0. Then we have wave function here. It goes to 0. And then we have wave function here. And that will be what we have right here, in fact. So we see we have wave function here, then this black part around it is where it goes to 0. Then we have wave function here, and then this black part around it goes to 0. Then we have wave function on the outside that then sort of decays off, and that's what we have going on right here. And so we can kind of keep going through this. So then we have the p orbital. So we have this lobe, and then it goes to 0, and then we have this other part of the lobe here. And so that is this right here, where we have this first lobe, then it goes to 0, and then we have this other part of the lobe. And of course we have we could add those m integers into it, into our total wave function here. We also have these m integers here, but those just tell us what the orientation of it is in space. So this is showing for m equals 0 and m equals 1. We would also have m equals -1, and that would be sort of going in and out of the screen. But anyway, I think I've rambled on about this long enough. I hope this helps you understand sort of the interpretation of these equations and how we actually get these sort of atomic orbital shapes that actually come out of the wave equations that we've been talking about in the past couple of videos. Once again, these are coming from the hydrogen atom. This is for the hydrogen atom, but it's going to look the same for the most part. It'll just be more sort of compactified, where this will not be this nice exponential decay. It'll actually go right to 0, where our R is equal to A, rather than having those exponential decays, because it'll be 0 everywhere where V is infinity, whereas in the hydrogen atom, it's sort of, we start from our radius, and then it's more of a gradual falling off of the potential. So the potential sort of gradually falls off, or I guess it would actually be more like it gradually increases as you go away, rather than just sort of going to the where it's A and then it immediately going to infinity. But anyway, like I said, the principle is still the same, and I'll talk about this stuff again when I actually get to this in the hydrogen atom, so I can actually talk about the equations that we're using here, which are the Laguerre polynomials. But anyway, I hope you found this video helpful, um, and I will see you in another video.